Hello everyone, welcome to today's video on the topic of trapezoidal rule. In this session, we'll learn about this numerical integration method and how is it derived from general quadrature formula. Let's get started. Let's quickly recall the Newton-Cotes general quadrature formula. This formula was derived from the definite integral of area under the curve. Here you can see that we have found the integral of fx dx from the limits x0 up to x0 plus nh, and the function fx is from y0 to yn. Note that here the points y0, y1, y2 up to yn are lying on the curve y or fx, and these are equidistant points. So you can see that on x-axis we have taken x0, x0 plus h, x0 plus 2h up to x0 plus nh. This equidistant property will also be used in the trapezoidal rule. We have already discussed the Newton-Cotes general quadrature formula and Newton forward interpolation method in previous videos. You can get the link of both the topics in the description box. Now let's learn about the trapezoidal rule of numerical integration. So what we have to do in the trapezoidal rule is that we have to put n is equal to 1 in the general quadrature formula, and then we have to neglect all the second and higher order degrees like delta square y0, delta cube y0, delta raised to the power 4 y0, and so on. So basically what we are doing here is that we are dividing the complete function fx into smaller subintervals of the trapezoidal form, and we will find the integration of each of this subinterval independently, and lastly we will sum up all these intervals. So first we will find the integration from x0 to x0 plus h, then we will find the integration from x0 plus h to x0 plus 2h, and so on till we have reached x0 plus nh. So let's now start with x0 to x0 plus h. To find this integral from x0 to x0 plus h y dx, we will put n is equal to 1 in the general quadrature formula. We will get h y0 plus half delta y0. Now we have to expand this delta y0 using the Newton forward difference table. We have already covered this topic in the Newton forward interpolation derivation part, and I will provide the link for the same in the description box. So you can see in this forward difference table that delta y0 is equal to y1 minus y0, which is the difference of these two. You can watch my previous video on the derivation for the Newton forward interpolation method. Now let's move back to the trapezoidal rule part. Here what we will do is we have to replace this delta y0 with y1 minus y0. So for the first trapezoid, we have found the integral as h y0 by 2 plus y1 by 2. In the same way, we will proceed to next trapezoids. So for the first interval, we have found the integral to be h times y0 by 2 plus y1 by 2. After this, we have to find the integral for the next limits, which is x0 plus h up to x0 plus 2h. Note that here we are using the equidistant points with the difference of 1h. So in the similar way, we can find the integration of this second trapezoid, and this integration will be h times y1 by 2 plus y2 by 2. In the same way, we have to move for the third interval. So integration of this third interval, which is from x0 plus 2h up to x0 plus 3h, will be h times y2 by 2 plus y3 by 2. Let's calculate the integral for the n minus 1th interval. Its limits will be x0 plus n minus 2h up to x0 plus n minus 1h. Its integration will be h times y n minus 2 divided by 2 plus y n minus 1 divided by 2. So let's calculate this integral for nth interval also. For the last interval, we will have the limits as x0 plus n minus 1h plus x0 plus nh. You can also see this from the diagram that the last trapezoid will be somewhere here and the limits of the integral will be x0 plus n minus 1h to the last one x0 plus nh. So the integral for this last trapezoid from x0 plus n minus 1h to x0 plus nh will be h times y n minus 1 by 2 plus yn by 2. Next, what we have to do is that we have to sum up all these smaller integrals to find the integral from x0 to x0 plus nh. For this, we will sum up all the smaller integrals which we have just found. So basically what we have to do is that we have to sum up all these integrals starting from the first interval and moving to the last one. We will add all the integrals vertically and we will get sum of all the smaller integrals which we have just calculated. Now we have to add these. Here you can see that h can be taken as common, y0 by 2 and yn by 2. These can be taken together and rest all the terms are y1 by adding these, y2 by adding these, and we can write it as h y0 plus yn by 2 plus y1, y2, y3 up to yn minus 1. So this is known as the trapezoidal rule. Here you can see that the first and the last term y0 and yn are written here and the remaining terms are written here. So we can rewrite this rule as integration of y dx from the limits a to b is equal to h by 2 sum of the first term and last term plus 2 times of sum of the remaining terms. So you have to remember this rule so as to solve all the examples. Let me sum up the trapezoidal rule for you. It is basically a numerical integration method in which we divide the complete interval into smaller subintervals. In this case, it is of trapezoidal form. As you have seen that first we integrated this subinterval, then we integrated this one up to the last subinterval, and in the last we have found the sum of all these smaller subintervals. By summing up the areas of these geometric shapes, which is trapezoid in this case, we can get an approximate value of the total area under the curve, which corresponds to the value of the integral. So this is it. This is the trapezoidal rule. We will also cover the examples of this rule in the next lectures. So stay tuned for the upcoming videos. If you have any doubts regarding the derivation part of trapezoidal rule, then you can ask in the comment section. Thanks for watching. Don't forget to like, subscribe and hit that bell icon for more such videos. Have a nice day.